Hi, AP Statistics. Today we're going to talk about Chapter 7, the intro to this, and it's called Random Variables. So we're still going to be dealing with probability, but we're going to narrow down our focus onto a specific type of variable. Okay, so a random variable is a variable whose value is a numeric outcome of a random phenomenon. Another definition is a numeric value whose value depends on the outcome of a chance experiment. Random variables are usually denoted by capital letters such as X or Y. Random variables are either discrete or continuous. So a random variable is discrete if its set of possible values is a collection of isolated points. On the number line. So in practice, a discrete random variable almost always arises in connection with counting. Okay, because when you're counting, you're only going to end up with a finite set where you can specifically count the number of items. So, for example, the number of items purchased. Like if you look at your grocery cart, you can count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, how many you have. The number of eggs broken in a carton, the number of gas pumps in use. These are all countable number of things. The number of students who are absent. We end up with just basically like integers. We're not having like 1.2 and 1.25 and 1.3, and you can go on and on and on with a continuous value forever. And so that's not what we're talking about. We're talking about a finite number of things. A random variable is continuous if its set of possible values include an entire interval on the number line. So a continuous random variable is one whose value is typically obtained by measurement. So the temperature in a freezer, for example, it doesn't have to be just like an integer for the temperature of a freezer. You could have, whatever it's supposed to be 0 degrees. You could have 0.1 or 0.15 and 0.2 and 0.21 and 0.22 and on and on and on. You're only limited by what you're measuring it by. So like the weight of a pineapple, again, you're only limited by what your scale can measure. But it's going to have take up an interval of values rather than a finite number of values. Okay, amount of time spent in a store. So again, those are all measurements. So this is your example of discrete, where you have a finite number of points. The possible values for a continuous, they take up a whole interval. You can have all the decimals and things in between, like two integers. Okay, so example 1, determine if each of the following random variables is continuous or discrete. Okay, so A, the number of defective tires on a car. Okay, so is that a countable number of things? Yes, so this is discrete. Or B, the body temperature of a hospital patient. Okay, so body temperature is being measured, and so that's going to end up being continuous. Okay, C, the number of pages in a book. Okay, that's a countable number of things, so this is going to be discrete. The lifetime of a light bulb. What do you think about that? Yeah, it's going to be continuous. Okay, it will take up an interval. It's not just, it's going to last whatever, 120 hours. It can go on and on. Okay. All right, discrete random variables. So we're going to talk about some details about discrete and then some details about continuous. So a discrete random variable x has a countable number of possible values. The probability distribution of a discrete random variable x lists the values and the probabilities that they have. So here's your example of just in general form. The value of x, you list the different values of x, and then the p are the different probabilities. So the probabilities, pi, so any of them, must satisfy these two requirements. Every probability is between 0 and 1, and the sum of the probabilities is 1. Okay, so if you sum them all up, you're going to have 1. Okay, so here's an example. Example 2. A consumer organization that evaluates new automobiles customarily reports the number of major defects on each car examined. A large number of automobiles were evaluated, and a probability distribution consistent with these observations is below. Let x denote the number of major defects on a randomly selected car of a certain type. Okay. So you've got our probability, the value of x, so this would be like 0 defects, 1 defect, all the way up to 10. And then the probability that each of these occur. So can you see how this is discrete? We're able to fit a table of values for all possible values. Okay. All right, so for these, they're pretty straightforward. Find the probability that there are more than 5 major defects. So we're still going to have probability notation. We're letting x be our variable. So we're going to say the probability x more than, so is greater than 5. Okay, so what are we going to do? We're going to look at, that would be 6, 7, 8, 9, and 10. So we're going to add up those probabilities. So 6 is 0.091, 0.046, 0.019, 004, 0.001. So go ahead and add those up. Okay. And so the probability x is greater than 5, you should get 0.161. Okay, so B, find the probability that the number of major defects is between 2 and 5 inclusive. So inclusive means you're including 2 and 5. So we've got probability 2 less than or equal to x less than or equal to 5. Okay, so that's the value 2, 3, 4, and 5. So we're just going to look at what's the probability of those occurring. For 2, it's 0.209. For 3, it's 0.223. 4 is 0.118. And 5 is 0.114. Okay, so you just sum those up in your calculator. So go ahead and do that. Okay, 0.734 is what you should get. Okay, and then for C, find the probability that there are at most 3 major defects. Okay, so at most 3, that is going to be 3 or smaller. So x is less than or equal to 3. Okay, so we're going to look at 0 is 0.041, 1, 0.046. Sorry, yeah. My last 2, 0.09, and 3 is 0.223. Okay, so go ahead and sum those up. So you should get 0.537. What I want you to notice is when you look in this table, what number of defects is most likely to occur? Where do you see most of the probabilities? Like the highest probabilities, where do you see those? Can you see that? Between like 2 and 5, seems like that's like the majority. Okay. So what we're going to start talking about is, on average, like how many defects do you think would occur? It's not necessarily just the middle number between 0 and 10. We're going to be looking at now what's the probability of each of them occurring and using the probability to figure out where the average is. Okay, because look, when you look at 6, 7, 8, 9, and 10, it's very unlikely to get that many defects. Okay, so the average is not going to be up there. But we'll talk about that more in class. Okay, example 3. Consider tossing a coin 5 times. What is the probability distribution of the discrete random variable x that counts the number of heads in 5 tosses of a coin? Okay, so on your test for chapter 7 and 8, you have a problem that is just like this, where you have to fill in the table. The values of x, okay, and then the probabilities, and then draw a histogram. Okay, it's a different problem, but it's the same type of thing. Okay, so we have a discrete random variable. It's our x that counts the number of heads. Okay, we're tossing a coin 5 times. So you could write out all of them, but that's going to be quite a pain. Because can we figure out how many different arrangements we could have? Think about it. I'm going to draw it over here on the side. 1, 2, 3, 4, 5. We're going to toss the coin 5 times. On the first toss, like think about mapping this out with like a tree diagram. On the first toss, how many options do you have? We have a head or a tail. Okay. On the second toss, you have a head or a tail. On the third toss, a head or a tail, head or a tail, head or a tail. So this is 2 to the 5th. Okay, so 2 to the 5th is 32. There are 32 different arrangements of heads and tails. I don't really want to write all those out. I don't know about you, but that's really annoying. Okay, so this is our total, is 32. We're going to learn some more strategies in chapter 8 on how to figure this out. But for right now, what I'm going to show you is, do you remember Pascal's triangle? Okay, Pascal's triangle, it's also like a combination is really what Pascal's triangle is basically doing. So if you want to think about a combination here, you get the exact same answer. So I'll show you both. So Pascal's triangle is 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1. So you're just adding the two numbers above it. So here 1 and 4 is 5, 4 and 6 is 10, 6 and 4 is 10, 4 and 1 is 5, and then it ends with a 1. Okay, so each of these rows, like we have 2 to the 5th, so we're in the 5th row is what we're doing. Okay, so if you had 2 to the 4th, you'd be in the 4th row. This just tells you the number of ways. So x is the number of heads. Okay, so let's start with, what are your options for x? The number of heads you could have. Okay, could you have one head and when you toss the coin 5 times? Yes. Could you have 2? Yes. 3, 4, 5. There's one other case that I didn't consider. It's 0. You can have a 0. If you have 0 heads, you had all tails. So the values of x that we can take on go from 0, 1, 2, 3, 4, 5. So that's the number of heads that you could have in 5 tosses of the coin. Okay, so this first one here, there's only one way to get 0 heads. That's just you have all tails. So here, this is one way out of 32. Okay, to get 1 head, there's going to be 5 ways that you can get 1 head. 5 different arrangements. Okay, for 2, there's 10. For 3, there's 10. This is just going across that row in the Pascal's triangle. For 4, there's 5. And to get all 5 heads, there's only one way to do that. So that's 1 out of 32. Okay, you can also think about this as a combination if you wanted to. If you like combinations, you like the way that works, you can pick any of them. So like if we look at 2 here, this is, we have 5 tosses of the coin, and I want to have it, and I want to select 2 in any order. Sorry, that kind of got crunched. But 5 combination 2 is 10. So that's what that will equal. If you look over here at 4, for example, you have 5 tosses of the coin, and you want to select 4 of them in any order. That equals 5. So if you want to think about it as a combination, it's perfectly fine. We're going to have some more strategies to solve this specific type of problem in chapter 8 that makes it a little bit easier. So I'm going to write these as decimals just so that it's a little bit easier to calculate. So 0, just 1 divided by 32. I'm going to have 0.03125. For 5 over 32, we have 0.15625. 2 is 0.3125, and 0.3125, 0.15625, 0.03125. Okay. Okay, so to draw out the probability histogram, this is just our x. These are the number of possibilities. So I'm just going to do 0, 1, 2, 3, 4, 5. And I'm going to just graph 0.3125. These are the probabilities. 0.15625. Okay, and we're just going to draw a histogram. So for 0, we're at 0.03, which is pretty small. 1, I'm up to 0.156. 2, I'm up to 0.3125. 3, I'm at the same height. 4, we're back down. 5, we're back down. Okay, so this was the probability. So that's what it means to draw a probability histogram. You just have the possible values for x and then the probabilities of obtaining those. So for C, find the probability of tossing at most 2 heads. So at most is less than or equal to 2. So now we can look back up on our table and we're going to add 0, 1, and 2. Okay, so we add those 3 up. So we get 0.5. Which you can tell at the table, it's half the table, okay, since it's symmetric. So find the probability of tossing at least 1 head. So at least 1, there's 2 ways that you can solve this. At least 1, you can scroll back up to the table a little bit. You can sum 1, 2, 3, 4, and 5. The other way you can do that is just subtract the 0. The 0 is the only one that you're not considering. So 1 minus 0.03125. Either way, whatever you want, however you want to solve it, you get this same result. I'm just going to do 1 minus the probability x equals 0. Okay, so 0.96875. But you get the same solution if you add 1, 2, 3, 4, and 5. The probabilities of each of those occurring. Okay. So discrete, you can write in a table, you can write out all the probabilities of each of the events. That's discrete, it's a countable number of things. We're going to switch and talk about continuous a little bit. So a continuous random variable x takes all values in an interval of numbers. The probability distribution of x is described by a density curve. Okay, do you remember the word density curve? We've seen that before. We had a specific type of density curve that we talked about a few chapters ago. A density curve, or a particular density curve, is a normal curve. So we're starting to talk about curves or area under the curve because it takes up a continuous interval. So that's kind of what a continuous random variable is about. So the probability of any event is the area under the density curve and above the values of x that make up the event. So here we start switching to area. Okay, so a little review of density curves. We've seen these before. All continuous probability distributions assign probability 0 to every individual outcome. Okay, so I'm going to talk about this for a second. Only intervals of values have possible probabilities. So what this means, okay, this is a kind of a huge part for this chapter. So put a star next to this. What this means is like when we're looking at like a density curve, it would be a normal curve. Do you remember that when we did like normal CDF or anything, we were always doing the area between two things, whether it went to positive infinity or if we were calculating the area between two things, we were able to do that. We always had to give it a left bound and a right bound because it's an area, okay, like area of a square. You do like or rectangle, length times width. You have to have two boundaries. So what this is saying is what if we just wanted to find the probability of one thing, like a line right here? That would just be one outcome. Does one outcome have any area? No, it doesn't. And like here, it has whatever you want to consider it, like a length, but it has no width. The width is 0. A line doesn't have area. So that's why in a continuous distribution, this would have probability 0 of this particular outcome because we need an interval. We need to go between two values to have area. So the probability of just one thing is 0 in continuous. Okay, so we'll kind of talk about that some more, but the area of one thing is going to be 0. Because the area of like one particular line doesn't have any value for a continuous random variable, we can write it with just strictly less than or equal to, and it's the same thing. Excuse me. That's not true for discrete. Like when we were in our table, we can tell the difference if we're including 2 or we're not including 2. We had those words inclusive because there's a big difference. But when we talk about continuous, there's no area for one line. So it doesn't matter which way you write it. Okay, all density curves have area area that are exactly 1 and do not go below the x-axis. It's only 0 and positive. So density curves can be any shape. They can be kind of some funky, skewed right, skewed left, any kind of. We've also saw broken line density curves. We've seen those before. Another specific type of density curve is the normal curve. It's a specific type of density curve with a mean mu and standard deviation sigma, also known as normal with mean mu, standard deviation sigma. That's shorthand notation. And what we did here was we used z-scores to find the area under the curve, okay, standardized values. So we're going to hit that up in just a second. Okay, so example 4, consider a random number generator on your calculator. If we allow it to generate a long sequence of numbers between 0 and 1, it will spread it out uniformly across the entire interval. So we want to find the probabilities. So here we have like from 0 to 1, and then these are the probabilities. Okay. So for part A, the probability x is less than 0.36. What that means is, like here, if this is 0.36, what's this area? Well, we're taking like the width times the height. Okay, so the height here is 1. So we're at 0.36 times 1, so it's just 0.36. Can I tell the difference between this less than 0.36 or less than or equal to? No, it's the same thing. So we have 0.36 here. All right, erase this. So over 0. Okay, so greater than 0.47. So 0.47 is going to be right about here. And we want it greater than. So my height is still 1, but what's this distance from 1 to 0.47? Yeah, it's 0.53. So we're going to do 1 minus 0.47, which is 0.53. Okay. Excuse me, sorry. All right, so I'm going to erase that. Do another one. 0.14 to 0.83. So we're in here between these two boundaries. So we're just looking at the difference between 0.83 minus 0.47, or sorry, 0.14, I looked at the wrong problem. And then we're still just timesing that by the height of 1. So we subtract that. What do we get? 0.83 minus 0.14, you get 0.69. So these won't always have a height of 1. It's just working out really nicely in this problem. That's not always true. Okay, so x less than 0.21. So we have this left side rectangle. And then or is greater than 0.68. Okay, so we're going to add those two things together. So area less than 0.21, so that's just going to be 0.21 times 1. Or, so we're going to add 0.68 to 1. What's that distance? Yeah, 0.32. Okay, so we add those together, you get 0.53. We can erase this. And then what's the probability it equals 0.72? Okay, so 0.72 is a line. Is there any area for that line? No. So make sure you can see that this is 0 here for continuous. Sorry. Okay. On August 31st, 2009, Gallup poll reported that 17% of Americans were worried about getting H1N1, which was the swine flu. Did any of you have swine flu? I don't know if you guys remember back that far, but my husband got it. He was one of the first in the area that we knew of, really, besides the volleyball girls who gave it to him. Yes, he had that in the summer, and then I got it in the fall, and so did like so many people. But anyways, okay. This proportion has approximately a normal distribution with a mean of 0.17 time and the standard deviation of 0.0097, where the population mean is 0.17 and the population standard deviation is 0.0097. A simple random sample is taken locally. Estimate the following sample proportions for p hat. Okay, so one thing we know, it's approximately normal. So I can draw a normal curve for this. It's just centered. Ooh, that's not a very good curve. Let's try that again. That's not really either. Okay, it's centered at 0.17. So it says, what's the probability the sample proportion is greater than 0.17? It's going to be this direction. Okay, do we remember if it splits it in half exactly? The area that would be to the right? Hopefully remember. So we can take our value, 0.17, minus the mean of 0.17, divide by our standard deviation. Oops. Okay, so this is going to be 0. Then what do? Normal CDF. Remember this? From 0 to positive infinity. So if you stick that in your calculator, or you can see the graph, what it's going to give us is 0.5. Okay, so we're pulling this probability. So this probability notation is new for us. But the rest of it is what we've calculated before. Okay, what's the probability that the sample... Oops, sorry, I don't know what I just did. I moved it to the top of the page. Sorry. What's the probability that the sample result will differ from the truth about the population by more than plus or minus 1 percentage point? Okay, so this type of question comes up where they give you by more than plus or minus 1 percentage point. Okay. So let's draw what this looks like. We're centered at 0.17. And so that's 17%, they said, of Americans were worried about getting it. So if we go more than plus or minus 1 percentage point, so 17%, if I go up 1%, I'm at 0.18. And if I go down 1%, I'm at 0.16. Okay. So now, oops, sorry, that's a little bit off, 0.18. Okay, what we can do, we want more than, we want it farther away, so either less than 0.16 or greater than 0.18 is what we're looking for. Okay, because we want it to be by more than. Be careful, because sometimes it'll say within 1 percentage point, and that would be between 16 and 18. But here we want more than. So first off, we're going to find two z-scores, one for 0.16. So we subtract the mean, 0.17, divide by our standard deviation. Okay, so we're going to calculate that, and then we also are going to do this for 0.18. Okay, so grab your calculator and find those two z-scores. Okay, you should get negative 1.03 and positive 1.03. Okay, now there's two ways that you can find this area. You can either calculate both of these tails, okay, so normal CDF from negative infinity to negative 1.03, and it's an or, so you're going to plus the normal CDF from the 1.03 to positive infinity. So you're going to calculate those tails and add them together. Can we see the other way that we could do this? Rather than calculate both, we know the area under the curve is 1, so you could do 1 minus the area between 16 and 18, which would be between negative 1.03 to positive 1.03. It doesn't matter how you calculate it, you get the exact same answer. Okay, so whichever way you choose to do it, go ahead and calculate that. Okay, so when you calculate it, you should get 0.303. However you calculate it, it will be the same. Okay, so what's the probability that the sample result will differ from the truth about the population by more than plus or minus 1 percentage point? That probability is 0.303. Okay, so the probability that the sample result will differ from the truth about the population by more than plus or minus 1% is 0.303. Okay, so we're kind of combining our probability understanding with now we're linking it back to what we covered with normal curves. Okay, so we'll talk more about this in class. Thanks.